Welcome to the Traffic Forecasting Volume Development video for the Missouri Department of Transportation. This video corresponds with the MoDOT Engineering Policy Guide, EPG 905.3. Let's begin with an overview and key takeaways for traffic forecasting and volume development. This module is broken out into 9 sections. All sections correspond to material available in the MoDOT Engineering Policy Guide, or EPG. This module starts with a high-level overview of traffic forecasting and volume development, and then transitions to a more focused look at traffic volume for a TIA. This video will cover these topics about traffic forecasting and volume development. Best practices for developing traffic volume estimates and forecasts to be used in the planning for and development of transportation projects. An understanding of how to compare before and after traffic conditions on road networks due to proposed land use changes, and a general process for how to determine if a proposed development should be added to a traffic forecast. To start, you'll need to understand the background of traffic forecasting. Let's focus on a few key national sources for requirements and/or best practices for traffic forecasting, including FHWA and NCHRP. Additional sources are listed at the end of this video. Even more sources are listed in the MoDOT Engineering Policy Guide. Accurate and timely traffic volume estimates are crucial for ensuring the success of transportation projects through each stage, including Transportation Impact Analysis, or TIAs. Traffic volume-based measures deal with the quantity of use of transportation facilities. The quantity can either be calculated at a specific point on a transportation network or between origins and destinations. Demand is associated with a specific time frame anywhere from 15 minutes to a 365-day annual period. Existing and future traffic volumes are necessary for most transportation projects and can be reported as daily volumes or hourly volumes. Capacity and safety analysis projects are examples of project types where daily traffic volumes are needed. Operational analysis projects are examples of project types where hourly traffic volumes are needed. Traffic forecasts are produced to assess transportation performance under different assumptions about transportation supply and demand. It uses existing traffic volume counts, historic traffic volumes, travel demand model projections, if available, land use plans, and socioeconomic data to predict traffic volumes and traffic flow patterns for a given year in the future. A traffic forecast is typically developed for a specific transportation project and is used for subsequent capacity analysis, geometric design, and pavement design. Now that we've discussed the background of traffic forecasting, it's time to learn about daily traffic volume refinement. AADT stands for Average Annual Daily Traffic. It represents the average traffic volume throughout the year considering typical traffic conditions. A true AADT is developed by using a full year of traffic count data, such as data generated from a permanent traffic counter, and dividing by 365 days. However, due to the limited number of permanent traffic counters, short-term traffic counts, usually a 24 to 48-hour period, are often used. When raw short-term traffic count data is collected, it should be processed by factoring it into average annual daily traffic, AADT, using factors that can be requested from MoDOT planning. Short-term traffic count data is converted to AADT by the following steps: applying an axle correction factor, ACF, adjusting to a typical weekday daily volume, and converting to AADT. Applying the axle correction factor, ACF. If the count method includes vehicle axle data, i.e. tube counts, then an ACF should be used to adjust the axle counts into vehicle counts. An ACF is developed from classification counts by dividing the total number of vehicles by the total number of axles. Partial weekday adjustment. If partial weekday data was collected, then an adjustment factor is used to convert partial weekday traffic count data to 24-hour weekday daily traffic volume estimates, also known as average daily traffic, ADT. The adjustment factor is representative of the percentage of 24-hour traffic volumes that typically occur on a weekday during the time range specified, for example 6 a.m. to 6 p.m. for a 12-hour traffic count. The adjustment factor usually varies by the type of roadway facility, for example interstate, U.S. route, or state highway. Average annual daily traffic. The ADT value is converted to AADT, which represents the average traffic volume throughout the year considering typical traffic conditions. Seasonal factors are used to convert ADT to AADT. For instance, ADT during a popular tourist traveling month, such as July, would have different ADT than a month with more typical travel patterns, such as April. Converting to AADT helps to account for these fluctuations based on the month of the year. This is how AADT can be estimated with short-term traffic counts, usually a 24 to 48-hour period, using the following formula. AADT equals ADT multiplied by the seasonal adjustment factor. We've discussed the daily traffic volume refinement. Now, let's discuss the design hour traffic volume refinement. For most analyses, design hour volumes, which are often AM and/or PM peak period traffic volumes, will be needed. Key phrases in this section include design hour, K-factor, and directional split. The design hour is a high-demand hour with a traffic volume used for designing the geometric and control elements of a facility. Often, this is the same as the AM and/or PM peak hour volume. The design hour selected will allow the designed facility to accommodate peak hour traffic during most days. The Highway Performance Monitoring System considers the hour corresponding to the 30th highest hourly volume of the year as the design hour as determined by continuous counters. In absence of continuous counters, local jurisdictions can adjust their design hour based on local facility-specific traffic conditions. The design hour volume, or DHV, represents the volume of vehicles that travel through a segment of roadway during the design hour. The formula for calculating the DHV using a design hour factor of K is DHV equals K multiplied by AADT. Design hour factor, or K factor. The design hour factor, known as the K factor, is the proportion of the AADT, average annual daily traffic, that occurs during the design hour. K factors are typically estimated to be between 8% and 12%, with lower K factors generally occurring on primary routes and higher K values occurring on secondary routes. In the absence of available traffic data, a planning level estimate of K equal to 10% is sometimes assumed for high-level sketch planning projects. Remember, the formula is K equals DHV divided by AADT. Another key consideration is the peak hour directional split, also known as the D factor. This is the percentage of the total two-way peak hour traffic that occurs in the dominantly traveled direction. For instance, a PM peak hour 55% D factor in the eastbound direction on a roadway means that 55% of all drivers in the PM peak hour are headed eastbound. We discussed the design hour traffic volume refinement, so now we are ready to learn how to balance traffic volumes. It's important to understand that raw traffic volumes along a corridor will have inconsistencies and differences when initially tabulated. Some typical reasons for base year traffic volume differences are other intersecting roadways along a corridor and traffic data collection method variations. For example, data collected on different days, counter error, and unexpected traffic incidents. Future year traffic volumes will frequently have inconsistencies due to varying growth rates applied along the corridor. So, you will need to consider how to balance this information. In this case, balancing traffic volumes means eliminating the traffic volume difference between multiple points completely. The graphic indicates an example of the result of balancing traffic volumes between 2 points. The NCHRP 765 states that balancing helps to clean traffic volume data by tempering the effects of outliers and counting errors. In the table shown, there are several methods to balance traffic forecast volumes. There are pros and cons with each method. While you are considering what method to use, it is important to understand the context of the project type and the context of the data collected to determine which volume balancing method is best. Ultimately, engineering judgment is recommended to determine which methods are appropriate based on traffic volume data available. For more information, visit the MoDOT Engineering Policy Guide. General rules of thumb are covered on the next slide. General traffic volume balancing rules of thumb are: understand the locations where data is more likely accurate, defensible, and verifiable by multiple sources. Rely on those data sources to carry forward traffic volumes during balancing. Balancing the project's needs between realistic results and efficient calculations. Be context sensitive to the level of analysis being completed and the appropriate level of effort and detail needed for traffic volume development and balancing. Determine level of error and if new data is needed. If the volumes are off by 10% or more, then review the data to determine if errors have been made in the data collection or processing.
Once you have balanced existing traffic volumes, you are ready to start projecting future traffic volumes using different types of traffic forecasting tools. It is important to understand the most appropriate tool to use for a traffic forecast. Consider whether it is a planning or design project, and consider the 4 factors listed here. The NCHRP 765 lists the 5 most common forecasting tools. 3 of these tools are growth rates, trend line analysis, and time series analysis. Each of these tools emphasize different things. The growth rate tool applies a constant growth rate over time. Trend line analysis uses historic traffic volume data to generate regression lines. Time series analysis extrapolates trends over time and can be either constant or variable in growth. These tools should be applied when no travel demand model is available. Historic growth in the study area is stable and expected to remain that way in the future. The project is small and low complexity, and resources and/or time are too constrained for more in-depth analyses. A potential shortcoming of these tools is that these methods do not naturally focus on the constraining factor of a roadway's capacity. This is an example of a trend line analysis regression line chart. The historic AADT values are displayed in tabular format and on the chart. In this example, the historic data goes back 20 years. There are different regression line options the user could choose to show for the available data, like linear and exponential. The regression lines are used to help determine the growth rate. In this particular example, the roadway facility has a 1.14% linear growth rate and a 1.12% exponential regression rate. Turning movement analysis is the process of analyzing, refining, and balancing turning movement count data for intersections studied as part of a traffic forecast. Apply this analysis when daily intersection turning movement counts are needed and/or design hour intersection turning movement volumes and factors are needed. A standalone turning movement analysis does not focus on base year to future year growth. Therefore, they are typically completed in conjunction with other tools. Travel demand models are the preferred tool for developing a traffic forecast if one is available for the study area. A travel demand model represents how choices are made when people travel. It combines a transportation system, or supply, with population and employment information by location, or demand for travel, and often encompasses a wide area, like a metropolitan region. It is important to note that a model is used to help develop a traffic forecast, but is rarely used as the forecast. The forecaster should use professional judgment, knowledge of local land use and travel patterns, and other tools to verify model results. Percentage changes from models may be more powerful than raw volumes. Travel demand models should be applied when a travel demand model is available for a region studied, generally within boundaries of an MPO. Growth in the study area is anticipated to change at varying rates relative to historic growth, and resources and the project schedule allow for model utilization. Travel demand models have some potential shortcomings. It is not always appropriate for projects of small size and minimal complexity. For example, a small bridge replacement project or site development project may not require a traffic forecast. A travel demand model can be calibrated for different conditions. For example, it could be developed to capture the accuracy of traffic conditions experienced in the PM peak, AM peak, or throughout the entire day. In some instances, a TDM may be calibrated to 1 or 2 traffic condition settings, but maybe not all. Model users should be cognizant of this when utilizing the model. There are several tools for developing traffic forecasts. Travel demand models are the preferred tool for developing a traffic forecast if one is available for the study area. Growth rates, trend line analyses, and time series analyses are all similar, but emphasize different things and can be applied when no model is available, growth is stable, the project is relatively small, and resources don't allow for an in-depth analysis. Additionally, turning movement analyses are typically completed in conjunction with other tools, like if approach and departure forecasts are known. Once you understand the types of traffic forecasting tools available, it is time to forecast traffic volumes. Before you begin the forecasting process, it is important to discuss the selected approach up front with the reviewer. It is important to establish expectations at the beginning and maintain constant communication and collaboration throughout all application steps. This is covered in more detail in the Project Needs and Scoping module. The development of traffic forecasts includes the following steps: collect and review data, develop base year no build or existing volumes, develop annual growth rate, develop future year no build forecast, develop base year and future year build forecasts, coordinate and review, and document. Step 1 is collecting and reviewing data. This consists of collecting data from the existing available data sources, such as the MoDOT Interactive Traffic Volume Map, developing historic AADT rates for data spanning 10 to 20 years of time, collecting project-specific traffic count data as needed, and converting raw project-specific daily count data to AADT estimates using seasonality and other factors. An example is provided of Main Street, which has the following data available: 48-hour tube count on the corridor west of Oak Street, 2020 AADT available between Oak Street and Pine Street, 2019 PM peak hour turning movement counts at the intersection of Main Street and Pine Street. Step 2 is developing base year no build traffic volumes. This step includes developing intersection turning movements, determining design data such as K and D factors and heavy truck percentages, and balancing traffic volumes between multiple intersections. In the Main Street example, 2021 PM peak hour traffic count data was collected at the Main Street's intersections with both Oak Street and Pine Street. The data was compared to the historic data and then refined so that the traffic volumes balanced on Main Street between the two intersections. Step 3 is developing the annual growth rate using a travel demand model if available. This consists of reviewing the model validation, comparing the existing model traffic volumes to actual project AADT estimates, reviewing the transportation network, ensuring accuracy of the model base year network relative to the actual transportation network, checking that all fiscally constrained MTP projects as identified by an MPO are included in the model's future year network, and calculating model growth, typically by dividing the future year model volume by the base year model volume. In the Main Street example, the compound annual growth rate was calculated between model traffic volumes in the model's base year scenario, 2018 in this example, and the model's future horizon year, 2045 in this example. This growth rate was then compared to a 10-year AADT historic trend line estimate for reasonableness. The model annual growth rate was 1.6%, and the historic trend line growth rate was 1.42%. Step 4 is developing the future forecast. Consider both model and historic AADT growth to determine and apply a growth rate to the base year no-build traffic volumes to estimate future year no-build traffic volumes. Then, review and adjust traffic volumes based on knowledge of future land use, professional judgment, and necessary volume balancing. In the Main Street example, a selected growth rate of 1.5% was determined based on the model, discussions with local planners and MoDOT, comparisons to other data sources, and engineering judgment. This selected value was applied to the 2021 balanced volume to estimate a 2045 future year no-build traffic volume of 1,494 vehicles in the PM peak hour. This was then adjusted to 1,500 vehicles during the process of balancing intersection traffic volumes. Step 5 is developing base year and future year build forecasts. Utilize the travel demand model when available to determine diversion and/or growth rates on the transportation network in the study area. If in areas without a model, use context-sensitive assumptions for the study area that are well documented. Apply the diversion to the no-build scenarios or the growth to the base scenarios to estimate build scenario volumes. Review and adjust traffic volumes based on knowledge of network changes, professional judgment, and to maintain reasonable corridor traffic volume balancing. In the Main Street example, the model's diversion rate of 22% was applied to the 2045 future year no-build balanced volumes to estimate a build scenario traffic volume. This would assume that the completion of the project would lead to a 22% increase in traffic volumes on Main Street. Step 6 is coordinating and reviewing. Coordinate with all appropriate parties and provide a review period to ensure that reasonable forecast assumptions are made. Refer to the MoDOT TIA Methods and Assumptions template available in the MoDOT Engineering Policy Guide 905.3 for appropriate parties to consider. In the Main Street example, the 2045 build traffic volume was adjusted during the MoDOT review process. MoDOT was able to remind the analyst of an anticipated development in the vicinity that would lead to an estimated 60 extra trips in the PM peak hour. This development was not included in the model, which is why it needed to be accounted for as an aside. The last step of the forecast application, Step 7, is documenting the forecast using a combination of figure diagrams and a report to explain all assumptions made. Refer to the MoDOT Methods and Assumptions Report checklist for topics to be included in the documentation. The checklist is available in the MoDOT EPG 905.3. Once you understand how to forecast traffic volumes, you can apply that knowledge to forecast volumes for a TIA. TIAs are engineering studies that compare before and after traffic conditions on road networks due to the proposed roadway network and/or land use changes. This section focuses on project-level forecasts that are primarily developed to support the creation of TIAs. The forecasting, scoping, and application steps of a TIA forecast will be similar to the forecasting steps listed on previous slides. However, additional focus should be provided on identifying potential new development traffic to add to the forecast. Exhibit 1 is provided on the next slide to help guide the user if a development should be added to the forecast. This decision flowchart is provided to help guide the user through the decision process if a forecast should be generated for a development. A larger version of the displayed Exhibit 1 decision flowchart is provided in the MoDOT Engineering Policy Guide. The flowchart asks key questions to determine if a development should be included in a forecast. Has a TIA already been developed and approved within the last 3 years? Will the proposed development generate 100 or more peak hour driveway trips? Will the development add 25 or more net new peak hour trips to the roadway facility? If the development is not included in the traffic forecast, then you are assuming that its future trips will be included and background growth of the forecast. To determine the impact that proposed developments will have on future traffic conditions, it is important to identify how development trips will be generated, distributed, and assigned on the roadway network. The following 5 steps are used to make this determination: assessing trip generation potential, determining mode split, estimating the generated trip types, distributing trips, and assigning trips. Step 1 is to assess trip generation potential. The most commonly accepted source for trip generation data on land use development is the ITE Trip Generation Manual. The ITE Trip Generation Manual includes trip generation characteristics of a wide variety of land use types. Trip generation characteristics for these land use types were developed based on studies completed from the year 1980 till now. Use the following steps to assess trip generation potential using the ITE Trip Generation Manual. Select an independent variable, such as the number of dwelling units, the number of residents or employees, or the square footage of businesses. Select an estimation time period. Typically, the AM or PM peak hour is selected. However, daily, weekday, Saturday, or Sunday values can also be chosen. Identify the setting of this development. Typically, general urban, suburban is the default setting. This exhibit is provided to help the user determine what trip generation method to use. A larger version of the displayed Exhibit 2 is provided in the MoDOT Engineering Policy Guide. Here are some key questions to ask yourself to determine what trip generation method to use. Has a compatible land use code been found that corresponds with the development being considered? Are there at least 3, but preferably 6 or more, data points for the land use code and independent variable selected? Is a fitted curve equation provided with an R-squared value that is equal to or greater than 0.75 and within the data cluster of the studies completed? Ultimately, you are trying to determine if the ITE Trip Generation Manual is appropriate or if local data collection is needed. If the ITE Trip Generation Manual is appropriate, then you are determining if the weighted average rate or the fitted curve equation is more appropriate. The second step in forecasting a TIA is mode split. The selection of trip mode choices should be informed by the availability of nearby transit and bicycle pedestrian infrastructure, a review of available multimodal count data, and coordination with local planning and engineering partners. Mode choice assumptions should be well documented in the final TIA. The third step is to estimate the generated trip types. The type of trips generated should be considered as part of the trip generation process. The total trips generated are determined, and then the internal trips, pass-by trips, and diverted link trips are subtracted to calculate new trips. New trips are primary trips that are made for the specific purpose of visiting the development. This trip type usually travels from an origin outside of the development to the development and then returns back to the origin. Trips that are made as intermediate trips on the way from an origin to a primary trip destination and do not require a route diversion from another roadway are called pass-by trips. Pass-by trips are new at the site driveway, but are not new on the adjacent roadway. It is recommended that pass-by trip percentages should only be applied to land uses numbered in the 800s for retail and 900s for services. Total pass-by trips should not exceed 10% of the volume on the adjacent street. For multi-use developments, pass-by percentages should be applied only to the retail component. An internal trip is a trip that both originates and ends within the development. Internal trip rates will vary depending on the proposed land use type, size, and the context of the surrounding area. For instance, a mixed-use development in an urban area would likely have a higher internal trip rate than a typical commercial development in a rural area. Internal capture rates may be estimated using an automated worksheet tool in the NCHRP 684. Diverted link trips are similar to pass-by trips in that they are attracted from nearby existing traffic. However, diverted link trips require a route diversion to a different roadway to reach the development, and they should be estimated only if reliable data from the percentage distributions of the three types of trips, primary, pass-by, and diverted link trips, are available for the land use being considered. It is recommended that the travel routes for diverted trips should be clearly established. Typically, the ingress and egress diverted link volumes are equal. The fourth step is trip distribution. The existing traffic patterns method is used for most TIA projects. This method derives trip distribution percentages based on existing data or data at sites that are comparable to the subject development. This method should be applied using the ITE trip generation manual and the existing traffic counts, combined with local knowledge of traffic patterns and land use. Other methods to be aware of, though not common for traditional TIAs, are the gravity model and socioeconomic data methods. These methods focus on traffic patterns from a regional and sub-regional perspective and are usually part of a complex computer model. The fifth and final step of forecasting TIAs is trip assignment. Trip percentage distribution is applied to the trips generated by the site for assignment of different trip types. Refer to the example on the following slides. You are now ready to review a TIA volume development example using the previously discussed topics. In this example, a new site will be connected to the intersection of Road X and Road Y by a new site driveway. In this first step, the new or primary trips will be calculated on the roadway facilities. In this example, the westbound to northbound right turn movement includes the following numbers and assumptions. The trip generation of the total outbound primary trips is 50. This comes from the ITE trip generation manual. The trip distribution of the outbound right turning primary trips is 40%. This is developed from existing traffic patterns as well as collaboration and communication with local planners and engineers. Based on these values, the trip assignment is 20 primary site trips that will make the westbound right turn. This slide displays the calculated assignment of primary trips for all applicable turning movements at the intersection of Road X, Road Y, and the site driveway using the method previously discussed. Pass-by trips are then identified for the roadway facilities. Exhibit 5 displays sample pass-by trip percentage assumptions. Typically, pass-by trips should not exceed 5 to 10% of the traffic volumes on the adjacent roadways. The egress and ingress pass-by volumes are usually equal. This is a continued example of pass-by trips. This slide displays the calculated assignment of both primary trips and pass-by trips for all applicable turning movements at the intersection of Road X, Road Y, and the site driveway. New site trips are shown in black and pass-by trips are shown in green. The northbound, southbound through movements have a loss of pass-by trips that are shifted to their respective turning movements headed into the site driveway. For example, the loss of 10 through trips headed northbound are replaced by the northbound right turn increase of 10 trips. Also, be aware of the pass-by trips exiting the site driveway, such as 10 trips making the westbound right-hand turn. This exhibit displays sample diverted link trip percentage assumptions. Note that egress and ingress diverted link volumes should be equal. Similar to the pass-by trips, the overall road-Y segment trips north and south of the intersection will contain a net gain of 0 pass-by trips if calculated correctly. The sum of the ingress trips equals 100%, and the sum of the egress trips equals 100%. This slide shows the previous steps in one graphic, as well as the calculated assignment of primary trips, pass-by trips, and diverted link trips for all applicable turning movements at the intersection of Road X, Road Y, and the site driveway. Pass-by trips are shown in green, while diverted link trips are shown in red. Note that the intersection will have a negative northbound-southbound through movement diverted link trips because they are now traveling into the site instead of traveling by. This exhibit displays site trip summation for Road X, Road Y, and the new site driveway. Each of the components of site trips are then summed for each vehicle movement and displayed in a flow diagram of total site trips. When you look at the westbound to northbound right turn movement, you will notice that 20 new site trips plus 10 pass-by trips plus 10 diverted link trips equals 40 total site trips making this turn. Site trips with background traffic for Road X, Road Y, and the new site driveway are now displayed. In looking at Exhibit 10, you can see that Road Y would have a total of 140 southbound through trips after subtracting 10 trips lost from what was originally 150 background trips. We just gave you a lot of information. Let's review the key takeaways included in this module. The best practices for developing traffic volume estimates and forecasts to be used in the planning for and development of transportation projects. An understanding of how to compare before and after traffic conditions on road networks due to proposed land use changes, and a general process for how to determine if a proposed development should be added to a traffic forecast.
Key additional sources are listed on this slide. Even more sources are listed in the MoDOT Engineering Policy Guide, or EPG. Time to see what you know. Please be aware that the quiz is designed to help reinforce module concepts and is not used to validate completion of the module. Question 1. What does AADT stand for? A. American Association of Driving Trucks. B. Average Americans doing traffic. Or C. Average annual daily traffic. The correct answer is C. AADT stands for Average Annual Daily Traffic. Question 2. K-factors represent the proportion of the AADT that occurs during the design hour. In the absence of available traffic data, a reasonable planning level estimate for a K-factor is A. 2%, B. 5%, C. 10%, or D. 17%. The correct answer is C. 10%. In the absence of available data, a reasonable planning level estimate for a K-factor is 10%. K-factors are typically estimated to be between 8% and 12%, with lower K-factors generally occurring at primary routes and higher K values occurring on secondary routes. In the absence of available traffic data, a planning level estimate of K equals 10% is sometimes assumed, for higher level sketch planning only. Question 3. There are 7 steps to traffic forecast application. What is the most important thing that parties involved in a forecast can do throughout all these steps? A. Develop K-factors, B. Utilize traffic simulation models, or C. Communicate and collaborate? The correct answer is C. Communicate and collaborate. This is the most important thing all parties involved in a forecast can do throughout the 7 steps to traffic forecast application. Before you begin the process, always discuss the selected approach up front with the reviewer. It is important to establish expectations at the beginning and maintain constant communication and collaboration throughout all application steps. This is covered in more detail in the Project Needs Scoping module. Question 4. The Institute of Transportation Engineers, ITE, has developed the ITE TRIP manual, which focuses on trip characteristics for various land use types. This manual includes studies on various land use types going back to 1980 to present. Is it A, distribution, B, generation, C, assignment, or D, diversion? The correct answer is B, generation. The Institute of Transportation Engineers, ITE, has developed the ITE Trip Generation Manual, which focuses on trip generation characteristics for various land use types. Question 5. For a TIA, new primary trips are trips that are made for the specific purpose of A. Diverting to a parallel route, B. Passing by the development, C. Representing all trips, or D. Visiting the development? The correct answer is D. Visiting the development. As previously discussed, new trips are primary trips that are made for the specific purpose of visiting the development. This trip type usually travels from an origin outside of the development to the development and then returns back to the origin. Thank you for participating in the Traffic Forecasting Volume Development module by MoDOT. This module corresponds with the MoDOT Engineering Policy Guide 905.3. MoDOT encourages you to view the other TIA guidance learning modules. If you have any questions, please reach out to MoDOT Central Office, Highway Safety and Traffic.